This is Rosen, Discrete Mathematics and its Applications, Section 2.2 on set operations. We are discussing set identities. Since set mathematics is another example of a Boolean algebra, we discussed Boolean algebras in Chapter 12 and propositional logic in Chapter 1 as other examples of a Boolean algebra. Set identities will look very similar to, in fact, analogous to the identities in those other two algebras. So let's take a look at these. So for A union, the empty set, we get A, and A intersect union, we get A back. If you want to go look at the propositional logic tables to find the analogies, think of the empty set as equivalent to the universal falsehood, since no element is a member of the empty set. And think of the universal set as analogous to the universal truth, since every element is a member of the universal set. Okay, domination laws. The union of A and the universal set gives the universal set. The universal set dominates in the union. The intersection of A and the empty set gives the empty set. The empty set dominates in the intersection. Idempotent laws. A union A is A and A intersect A is A. Complementation laws is similar to the law of double negation. The complement of a complement returns the original. The union and the intersection operators commute. Doesn't matter the order. And they're also associative if you have a string of unions and a string of intersection. It doesn't matter in which order you do those operations pairwise. And distributive laws also apply. The distribution of intersection over union in the first line, and the distribution of union over intersection in the second line. A intersect B union C gives us A intersect B union with A intersect C, and similar for the next line. All of these things can be proven in a couple of ways, as we'll see in a little bit, but a few more identities are before us. De Morgan's laws. Remember, we've had De Morgan's laws in the preceding algebras, and so we'll still have them here as well. What do they look like? The complement of A union B is equal to the intersection of the complements, and the complement of the intersection of A and B is equal to the union of the complements. Absorption laws. A union A intersect B gives A, and A intersect A union B gives A. And finally, complement laws. A union A complement gives us the universal set, and A intersect A complement gives us the empty set. In other words, a set is always disjoint with its complement. All right, how do we prove these? Well, we proved them in propositional logic using a truth table, and also in Boolean algebra using a Boolean table. We'll see there's a similar approach as well, but there are other approaches too, using what we know from set properties. Okay, since these are sets on either side of the equal sign, we can use the rule that to show that two sets are equal, show that each is a subset of the other. We could use set builder notation in propositional logic. And then we can use what's called a membership table, and this is an exact analogy to a truth table or a Boolean table. In order to construct a membership table, we think of an arbitrary element X in all possible combinations of the base sets that we're combining to create a new set with the operations. And in all the ways that either belongs or does not belong to both sides of the identity. And you're going to use a 1 to indicate that it is in the set and a 0 to indicate that it is not in the set. All right, so let's take a look at a proof of the distributive law of union over intersection in this case. So I'm going to consider an arbitrary element x, and I'm going to have three underlying sets. So I'm going to have 8 rows because there are 8 different ways that an x could be or could not be a member of those 3 sets. And so when I construct the table, I'll have all of these sets over here. And here are all the 8 ways that x can be a member or not a member of the 3 sets simultaneously. It's a member of all of them, of only A and B, of only A and C, of only A, of only B and C, of only B, of only C, and a member of none of those sets. And you can see that the table is constructed just like a truth table or a Boolean table, where we have 4 ones and 4 zeros in the first column, 2 ones, 2 zeros, 2 ones, 2 zeros in the second column, then 1 0, 1 0, 1 0, and so forth in the third column. And that gives us all combinations of possible inclusion in those 3 sets. And now we can do the set operations for portions of these sets and build up. So in the first case, we'll do B intersect C, and we see that if an element is in set B and in set C, it'll be in the intersection of B and C. If an element is in set B and not in set C, it will not be in the intersection of set C, and so forth all the way down. And then when we're doing this column here, A union B intersect C, we're looking at that column that we just created and A to see to build the inclusion table or the inclusion values for that set. And we end up getting, for our 8 combinations, 5 ones and 3 zeros in succession. Do the same thing for A union B and A union C in these columns, and then take their intersection to get the exact same inclusion pattern. So that means that these 2 sets are equal. And that is a membership table approach to proving identities.